Hi guys, and welcome to a new lesson and section, and this is called data management with SQL. We are going to get into the structured query language, and so in this section you are going to be introduced to some of the concepts behind SQL and relational databases. You will find out how to use SQL to create data tables and populate them with data, and how to manipulate the data contained within those tables. You're going to link tables to capture the relationships between data, and finally apply all of these techniques to our lending library. So let's go over some relational database concepts first. The basic principle of a relational database is very simple. It's simply a set of two-dimensional tables. Columns are known as fields and rows as records. Field values can refer to other records, either in the same table or in another table. That's the relational part. So an example can be a table holding data about employees. The upper table is about employees, and on the bottom here it's salary data. So on the first table, notice a couple of conventions demonstrated by this data. You have an identifier field to uniquely identify each row. This ID is known as the primary key. It is possible to have other keys too, but conventionally there is nearly always an ID field to uniquely identify a record. In this case is the employee ID. This helps should an employee decide to change her name, for example. And you can link one row to another by having a field that holds the primary key value for another row. Thus, an employee's manager is identified by the manager ID field, which is simply a reference to another emp ID entry in the same table. So looking at your data, you see that both Fred and Anne are managed by John, who is in turn is managed by someone else, whose details are not visible in this section of the table. And also want to mention something called relationship cardinality. Relationships within a database link two or more entities together. The number of each entity involved in the relationship is known as its cardinality. The relationships can be one-to-one, where one record links to exactly one other record. They can also be one-to-many, such as the employee to manager relationship in the example that we saw. A relationship can also be many-to-many. This relationship is best explained by an example that we will get back to later. Suppose you Suppose you introduced a new table of tasks. Each task could have many employees assigned to it. At the same time, each employee could have several tasks. There is therefore a many-to-many relationship between employees and tasks. Much of the work in any database application is focused on maintaining the many-to-many relationships within the database. Several forms of graphical notation, known as entity relationship diagrams, are used to describe database structures. Most of these notations have a strong emphasis on showing the cardinality of each relationship. And back to the tables, you are not restricted to linking data within a single table. We can create another table like we have done here, like salary, A salary can be related to grade, so we can get a second table like the salary table. To determine employee John Brown's salary, you first look up John's grade in the main employee data table, and you would then consult the salary table to learn what an employee of that grade is paid. Thus, you can see that John, a foreman, is paid $60,000. Relational databases take their name from this ability to link table rows together in relationships. Other database types include network databases, hierarchical databases, and flat file databases, which includes the DBM databases we looked at earlier in this section. For large volumes of data, relational databases are by far the most common, and you can do much more sophisticated queries too, and you look at how to do this in the next few sections. But before you can query anything, you need to create a database and insert some data. That's what we're going to do. We are going to talk a little bit about structured query language, also shortened for SQL. The structured query language, or SQL, pronounced either as SQL or the letters SQL, is the standard software tool for manipulating relational databases. In SQL, an expression is often referred to as a query, regardless of whether it actually returns any data. SQL is comprised of two parts. The first is the data definition language, DDL. This is the set of commands used to create and alter the shape of the database itself, its structure. DDL tends to be quite specific to each database, with each vendor's DLL having a slightly different syntax. The other part of SQL is the data manipulation language, DML. DML, used to manipulate database content rather than structure, is much more highly standardized between databases. You spend the majority of your time using DML rather than DDL. So in this course, we use the SQLite database, which has three big advantages. First, it has an API module provided as part of Python's standard library. Second, it is a simple dialect of SQL to learn. Third, and by no means least, SQL works from a single data file and code library, so you don't need to set up a database server or worry about any of the database administration duties normally associated with maintaining relational databases. And we will only look briefly at DDL, just enough to create with the create command and destroy with the drop command our database tables, so that we can move on to filling them with data, retrieving that data in interesting ways, and even modifying it using the DML commands insert, select, update, and delete. So to use the SQL interactive prompt, you need to download the SQLite interpreter because it does not come with Python. You can find it on the SQL website that I'm showing you right now, sqlite.org/download.html. The version may not match exactly, but the database format is sufficiently stable that the latest interpreter can generally be used with the Python SQLite 3 module without difficulty, although the versions might not match exactly. You only need to download the binary for your OS labeled shell. The libraries are already installed with Python. Linux users can usually find SQLite in the package manager, and this is the easiest way to install it if available. Okay, what you need to download is this file. This is, I'm now showing you 29th of December 2016. What I had to do, I had to download this file and this file, this zip file, these two zip files, because I'm on 64-bit, and you have to find out which one of these you need to download. This one you have to download, and one of this. And when you unpack it, let me check. When you unpack it, you have to create a folder on your C drive, like I've done, SQLite here, like I've done here, and name it just like this. And when you unpack it, you have to have these 3 files installed in this root folder here. So do exactly like this. If you're on Windows, you have to unpack all the files, and you have to collect these files and put it here. Otherwise, it won't work as I am showing you. So just do as I have done. If you know other ways, you can do that, but if you want to follow the tutorial as I have done it, so do it like this. And then you need to set your environmental variables. So just hold the Windows key and pause break key, and it will bring you the system dialog window, and you go to advanced system settings and go to environmental variables, go to path, and create a new value, and create a new value like this, like these values here, C:\/ SQLite, exactly as I have done it. Follow the uppercase, it's case sensitive, I found out. And put an environment variable there, so that you are able to use SQLite database from the command prompt in Windows. So once you have done that, you may need to restart your Windows and to get it to work. So just make sure that you have that working. So creating tables. To create a table in SQL, you have to use the create command. It is quite easy to use and takes the following form, as you can see on the foil here: create table, and then table name and the field names. So one thing to note is that SQL statements in the interpreter must be terminated with a semicolon. This is because SQL statements can span multiple lines, so the interpreter needs to be told when you are done. SQL executed by Python code is passed as a single complete string, so a closing semicolon is not necessary. And SQL is not case sensitive, and unlike Python, does not care about whitespace or indentation levels. An informal style convention is used, but it is not rigidly adhered to, and SQL itself cares not a jot. So let's now try to create our employee and salary tables in SQLite. The first thing to do is to start the interpreter, and which you do simply by invoking SQLite 3. This is the command with a single line argument, the data and the database file name. And if that database file exists, the interpreter will open it. Otherwise, it will create a new database file by that name. If you omit the database file name entirely, the interpreter will still process your commands, but your data will exist only in RAM and will disappear irretrievably when you exit the interpreter. So let's create the employee database, and just let me move to the correct to the correct folder. Now we're in the folder so at the current moment we don't have any db file here, so let's create a file called employee.db. So if you look at our so the interpreter creates an empty database called employee.db and leaves us at the SQLite prompt, ready to type SQL commands. We are now ready to create some tables, so let's do that. And I haven't used a semicolon yet, so because I'm going to type some more data. So now we have created the first table, which is employee table. Let's create another one. And we are just following these examples here. Let's look at the tables we have created. Okay, so note that you move the list of fields into a separate line, making it easier to see them. The fields are listed by name but have no other defining information such as data type. This is a peculiarity of SQLite. Most databases require you to specify the type along with the name. It is possible to specify types in SQLite too, but it is not essential at this moment. We will look at this in more detail in later section. Also note that we tested that the create statements had worked by using the .tables command to list all the tables in the database. The SQLite interpreter supports several of these commands that we use to find out about our database. .help provides a list of commands along with a brief description of their function. So here's the help function. So if you're stuck, just use the help .help command. You can do lots of other things when you create a table, as well as declaring the types of data in each column. You can also specify constraints on the values. Constraints are rules that the database enforces to help ensure the data remains consistent. For example, not null means the value is mandatory and must be filled in, and unique means that no other record can have the same value in that field. Usually you specify the primary key field to be not null and unique, or you can also specify which field is a primary key, and we will look more closely at these advanced creation options later in the section. And SQLite provides a model set of constraints that you can apply. Some commercial databases provide very rich and powerful constraint options, and it is tempting to use constraints to implement much of the business logic around the data. This is usually a mistake because it forces you to insert or modify your data in a particular order, which can become increasingly difficult to figure out. It is best to keep constraints for controlling data integrity and build the application logic into the program code. And for now, we leave the basic table definition as it is and move on to the more interesting topic of actually creating some data. So let's look at how to insert data. And this is how we insert data into a table. And the structure is very simple, almost same as create. And an alternate form of insert uses a query to select data from elsewhere in the database, but that's too advanced at this stage. And you can read about it on the SQLite manual, which you can find on their website, which is SQLite.org. And in order to insert some rows into our employee tables, you can follow along and do as I'm doing. This is the same data that we have on this example here. The hire date. That was the first row. And then we have to repeat it again for the next employee. I'm just going to cheat a little bit. One, two, three, four. I think it's been a mistake here. Okay guys, a small quotation error. So let's try this again. So I'm inserting into employee these values. Excuse me. And also spelling should be correct. There we go. Now we need to insert Fred Smith. Let me just find that Fred Smith. There's Fred Smith. Same goes here. There we have our employees. We need to add one more. We need to add Anne. Has the same manager ID. Let's see, we have three employees, and now for the salary table we have to update that as well. And let's now add another salary. For the laborer, it should be 35,000. Semicolon. Okay, and that's it. We have created two tables and populated them with data corresponding to the values described in these examples. Notice that we use actual numbers of the salary amount, not just string representations. SQLite tries to determine the correct data type based on the insert input values we provide, because it makes the most sense to have SQLite maintain salary data as a numeric type. It behooves you to inform SQLite of that preference in your insert statements by specifying salary data in numeric, not string format. So now we are ready to start experimenting with the data, and that's when the fun starts. Not just fun when I'm typing things wrong. So let's talk about reading data. We read the data by using the SQL's select command, as I have shown you a couple of times here. And select is the very heart of SQL and has the most complex structure of all the SQL's commands. You start with the most basic form and add additional features as we go. So this is the basic select statement, and it selects everything from a table. So that's the special wildcard character, the star, instead of a list of fields, names to return of all the fields. We should only use this when working at the interactive prompt. If we were to use it in an application code and someone later added an extra column to the database, your application would break. By specifying the exact fields to be returned, your code becomes much more resilient to changes in the database. So let's try on some other variations. let's, for example, try to select names of all employees in our database. Then you get all the names. And in this case, that's the only 3, but if we have a bigger database, that's probably going to be more information than you want. To restrict the output, you need to be able to limit your search of sometimes. SQL enables us to do that by adding where clause to our select statement. So the condition is an arbitrarily complex Boolean expression that can even include nested select statements within it. And let's try that with where clause to refine our search of names. This time we'll only look for name of employees who are laborers. Then we get back Fred and Anne who has a employee grade of laborer. We only get 2 names back, not 3, because John Brown is not a laborer. And we can extend where condition using Boolean operators such as and, or, not, and so on. Note that the equal in a where condition performs a case-sensitive test. When using the equal test, the case of the string is important. Testing for laborer with lowercase would not have worked. SQLite has some functions that can be used to manipulate strings, but it also has a comparison operator called like that uses percentage sign as a wildcard character for more flexible searching. So let's give an example of that with the like statement. So after converting grade to lowercase, we then tested it for an initial substring of lab. When used in conjunction with lower or upper function and SQLite's other string manipulation functions, like can greatly increase the scope of your text-based searches. The SQLite documentation has a full list of the functions available. So, and one note is that you can test out the SQLite functions in the interpreter using the following technique. In a select statement, the return value can be any expression and the table clause can be empty. By combining these 2 features, you can write code like select and lower parentheses Freddy in quotes, Freddy, for example, a name, and SQLite returns the value Freddy in lowercase. This is very useful when you want to quickly experiment with a function to see what it does. So notice too that in the where clause, you use dot notation, for example in employee.grade, to signify the grade field. In this case, it was not really needed because you were only working with a single table, employee, as specified in the from clause. But where multiple tables are specified, you need to make clear which table the field belongs to. As an example, we can change our query to find the names of all employees paid more than $50,000. So to do that, we need to consider data in the both tables. So we can use it like this. And as expected, you get only one name back, that of the foreman. But notice that you also got back the salary because you added amount to the list of columns selected. Also note that you have two parts to our where clause combined using an and Boolean operator. The first part links to the two tables by ensuring that the common fields are equal. This is known as join in SQL. A couple other features of this query are worth noting. Because the fields that you are selecting exists in two separate tables, you have to specify both of the tables from which the result comes. The order of the field names is the order in which you get the data back, but the order of the tables doesn't matter so long as the specified fields appear in those tables. We specify two unique field names so SQLite can figure out which table to take them from. If you had also wanted to display the grade, which appears in both tables, we could have used the dot notation to specify which table's grade we wanted. And we could do that. I'll just show you an example of how we could do that in Notepad. And let's say this is a prompt of SQLite, and it then like this. So note in particular that SQL would require such qualification, even though the choice of table here for the grade field really does not matter, because the where condition guarantees that for any result row displayed, the grades of the two tables will have the identical value in any case. The final feature of select that we are going to discuss, you can also read more on the SQL documentation for select, is the capability to sort the output. Databases generally hold data either in the order that makes it easiest to find things or in the order in which they are inserted. In either case, that's not usually the order you want things displayed. To deal with that, you can use order by clause of the select statement. And the general way of doing that is something like this. So notice that the final order by clause can take multiple columns. In this case, we have primary, secondary, tertiary, and so on sort orders. So we can use this to get a list of names sorted by the hire date from our small database. So it is interesting to know that hire date was perfectly acceptable as an order by column, even though hire date is not a column selected for display. And that's really all there is to it. You can't get much easier than this. The only thing worthy of mention is that we didn't use a where clause. If you had used one, it would have had to become before the order by clause. Thus, although SQL doesn't require that all components of a select statement to be present, it does require that those elements that are present will appear in a pre-described order. And that's enough about reading data, and we'll look at how to modify the data. So modifying data, you can change the data in our database in two ways. You can alter the contents of one or more records, or more drastically, you can delete a record and even the contents of a whole table. Changing the content of an existing record is the more common case, and we do that by using the SQL update command. So the basic format of updating is shown here. I'm just writing pseudocode so you understand what I'm trying to say. So this is the format. So we can try it out on our employee database by changing the salary of a foreman to 70,000. Let's update it to 70,000. So be careful to get the where clause right. If you don't specify one, every row in the table is modified, and that's not usually a good idea. Similarly, if the where clause is not specified enough, you end up changing more rows than you want. One way to check if you have it right is to do a select using the same where clause and check that only the rows you want to change are found. If all is well, you can repeat the where clause from the select in your update statement. A more drastic change you might need to make to your database table, rather than merely modifying certain fields of a given row or rows, is to entirely delete one or more rows from the table. And you would do this using the SQL delete from command, whose basic forms looks like the pseudocode again. And so if we want to delete Ann Jones from our employee data table, then we can do this. And Ann is gone. If more than one row matches your where condition, all of the matching rows are deleted. SQL always operates on all the rows that match the specified where condition. In this respect, SQL is quite different from, say, using a regular expression in a Python program to perform substring substitution on a string, where the default behavior is to modify only the first occurrence found, unless you specifically request otherwise. An even more drastic change you might want to make to your database is to delete not only all of a table's row, but to delete the entire table itself. This is done using SQL's drop command. Obviously, destructive commands like delete and drop must be used with extreme caution. So now let us look at linking data across tables. So the possibility of linking data between tables was mentioned earlier in the section on select. However, this is such a fundamental part of relational database theory that you consider it in a more depth here. The links between tables represents the relationships between data entities that give a relational database, such as SQLite, its name. The database maintains not only the raw data about the entities, but also information about the relationships. The information about the relationships is stored in the form of database constraints applied when you define the database structure using the create statement. Before we see how to use constraints to model relationships, we need to look deeper into the kinds of constraints available in SQLite. So just showing an example, let's look more into the data constraints. We normally express the constraints on a field by field basis within the create statement. So we can expand the basic definition from this first line into this line. And the most common constraints are not null, primary key, which is also incremented, unique, and default value. Not null is fairly self-explanatory. It indicates that the value must exist and not be null. A null value is simply one that has no specified value, rather like none in Python. If no suitable value is provided for a field governed by a not null constraint, data insertion will utterly fail, quite possibly not only for that particular field, but also for the entire row. Or far worse, violation of the constraint could cause a very large database update transaction, possibly involving hundreds of thousands of rows, to fail in its entirety. Primary key tells SQLite to use this column as the main key for lookups. In practice, this means it is optimized for faster searches. The optional auto-increment keyword means that an integer type value is automatically assigned on each insert and the value automatically incremented by 1. This saves a lot of work for the programmer in maintaining separate counts. Note that the auto-increment keyword is not only used, rather it is implied from a type constraint combination of integer primary key. This not so obvious quirk of the SQLite documentation trips up enough people for it to appear at the top of SQLite frequently asked questions page. The unique constraint means that the value of the field must be unique within the specified column. If you try to insert a duplicate value into a column that has unique constraint, an error results and the row is not inserted. Unique is often used for non-integer type primary key columns. Default is always accompanied by a value. The value is what SQLite inserts into that field if the user does not explicitly provide one. So let's try it with a short example showing some of the constraints. So if we exit and create a new database just called test.db, Sorry about that. I'll explain in a minute. Excuse me. Showing different way of inserting data. So the first thing to notice is that although none of the insert statements had an ID value, there is an ID value in the select output. That's because by specifying ID to be an integer primary key, it is automatically generated by SQLite. Notice too how the entry of header has the default value set. Also note that the value of Linda is non-existent. Sorry, Laura, or null. There is an important difference between not null and default. The former does not allow null values either by default or explicitly. The default constraint prevents unspecified nulls, but does not prevent deliberate creation of null values. You can also apply constraints to the table itself, such as how to handle data conflicts like duplicates in a unique column. For example, a table constraint could specify that where a conflict occurs, the entire database query will be cancelled, or it could specify that only the changes to the conflicting row be cancelled. Table constraints are not discussed further in this section, so just consult the documentation for details. And also I'd like to talk about data SQLite field types. The other kind of constraint that we can apply are, as already mentioned, is to specify the column type. This is very like the concept of data types in a programming language. The valid types in SQLite are text, integer, real, numeric, blob, null. And these types should be self-evident with the possible exception of numeric, which enables the storage of floating point numbers as well as integers, and blob, which stands for binary language object, typically used for media data such as images. Null is not really a type, but simply suggests that no explicit type has been specified. Most databases come with a much wider set of types, including, crucially, a date type. And SQLite has a somewhat unconventional approach to types that renders such niceties less relevant. One note is that SQL standard, having been defined by a committee including many database vendors with existing products, is very broad in its list of types. SQLite tries to accommodate this by aliasing several different names to the same underlying type. Thus, the native text type can also be expressed as a string or as a var_char. Because these are terms used by other vendors, the idea is that porting SQL code from another database to SQLite should be as painless as possible. And most databases strictly apply the types specified. However, SQLite employs a more dynamic scheme where the type specified is more like a hint, and any type of data can be stored in the table. When data of a different type is loaded into a field, SQLite uses the declared type to try to convert the data, but if it cannot be converted, it is stored in its original form. Thus, if a field is declared as integer, but the text value 123 is passed in, SQLite converts the string 123 to the number 123. However, if the text value, in example Freddy, is passed in, the conversion fails. So SQLite simply stores the string Freddy in the field. This can cause some strange behavior if you are not aware of this foible. Most databases treat the type declaration as a strict constraint and fail if an illegal value is passed. So the next thing I wanted to talk about is modeling relationships with constraints. So let's look at our tables again. Having seen the various kinds of constraints available and how you can use them in your database, it's time to return to the topic of modeling relationships. So how do constraints help you to model data and in particular relationships? So looking at these tables and looking at the employee table first, we see that emp ID value should be of integer type and have a primary key constraint. The other columns, with the possible extension of the manager ID, should be not null. Manager ID should also be of type integer. And for the salary table, we can see that once more the salary ID should be an integer with primary key. The amount column should also be an integer, and you should apply a default value of, say, 20,000. Finally, the grade column should be constrained as unique because you don't want more than one salary per grade. And actually this is a bad idea because normally salary varies with things like length of service as well as grade. But let's just ignore these things for now. And in the real world, you should probably call this a grade table and not salary. So if we had to use SQL on this, it looks like something like this, where we create the table and we will put the constraints on the different fields. The first one is on the table employee, and the next is on salary. You can try out this constraint by creating a test DB or on the test database that we created earlier, and just create a new table in there. You can try out this constraint by attempting to enter the data that breaks them and see what happens. Hopefully you'll see an error. And one thing to point out here is that the insert statement that we used previously are no longer adequate. We previously inserted our own values for the ID fields, but these are now auto-generated, so you can and should omit them from the inserted data. But this gives rise to a new difficulty. How can you populate the manager ID field if you don't know the ID of the manager? The answer is that you can use a nested select statement. And we are going to see in this example now that we do this in 2 stages, using null fields initially and then using an update statement after creating all the rows. And to avoid a lot of repeat typing, you can put all of the commands in a couple of files called employee SQL. You can find that file called employees.sql, this file, in the zip file or rar file I have provided you with. So if you go and take that file and put it in the working folder, this is just to avoid a lot of repeat typing. And this employee SQL is for the table creation commands. And you have another file in the SQL folder, which is called load employees SQL. Also take that and put that in the current working directory. And what load employee.sql does is for the insert statements. So this is the same idea as creating a Python script file ending in .py to save typing everything at the prompt. So the SQL employees SQL file looks like this. And notice that we drop the tables before creating them. The drop table command, as mentioned earlier, deletes the table and any data within it. This ensures the data is in completely clean state before we start creating our new table. You will get some errors reported the first time you run this script because no tables exists to drop, but just ignore them. Subsequent execution should be error-free. And the load employee SQL file looks like this. And notice the use of the nested select statement inside the update command, and also the fact that you use a single update to modify both employee rows at the same time by using the SQL in operator that works like the Python in keyword for testing membership of a collection. By extending the set of names being tested, you can easily add more employees with the same manager. This is typical of the problems you can have when populating a database when constraints are being used. You need to plan the order of the statements carefully to ensure that for every row that contains a reference to another table, you have already provided the data for it to reference. It's a bit like starting at the leaves of a tree and working back to the trunk. Always create or insert the data with no references first, then the data that references that data, and so on. If you are adding data after the initial creation, you need to use queries to check that the data you need already exists, and add it if it doesn't. At this point, scripting language like Python becomes invaluable. So at the SQL prompt, let me just exit and get into the employee database. typos. Let's check. We have some tables here, and we have some data in it. So what we are going to do, we are going to read those read the data from the SQL files. It didn't give me the errors that I talked about because the tables exist. That's why it's just dropping. So make sure you have the path issues sorted out though. Either start SQLite 3 from wherever the .SQL scripts are stored, as I mentioned, or provide the full path to the script. I prefer to starting on wherever the SQL scripts are stored. Let's now try to check that everything is as it should be. Excuse me. Just have to so I had a little typo again. So the last part on that you see in the bottom, that seemed to work. John Brown is the only employee earning more than 50,000. Notice that we used an in condition combined with another embedded select statement. This is a variation on a similar query that we performed previously using a cross-table join. Both techniques work, but usually the join approach will be faster. Although this is an improvement over the original constrained definition and it ensures that the manager ID is an integer, it does not ensure that the integer is a valid emp ID key. You need the embedded select statement for that. However, SQLite offers one more constraint that helps you ensure the data is consistent, and that is the references constraint. This tells SQLite that a given field references another specified field somewhere in the database. You can apply the reference constraint to the manager ID field by modifying the create statement. And we can do that by in this way, by updating, modifying the create statement like this. And you see that the references constraint specifies the table and the key field within it. At the time of this course, SQLite does not actually enforce this constraint by default, although it is worth including in your code as documentation of your intentions. However, you can turn checking on by using a pragma statement. Pragma is a special command that is used to control the way the interpreter works. So if we saw our employee SQL, it already has the pragma foreign key equals true. The term foreign key signifies that it is a key from a different row in the database. This could be a key from the same table, as in the case of the manager ID, or it could be a reference to another table entirely. In either case, the key being referenced comes from a different row and is therefore described as being foreign. So let's now try if these restraints will work. The example that we already have. Let's try to insert some new data. So this is a big advantage in keeping your data consistent. It is now impossible for a non-valid worker to manager relationship to be created, although you can still use null values that indicate that no manager relationship exists. So and the next thing I'm going to talk about is the many-to-many relationships. So one scenario we haven't covered is where two tables are linked in a many-to-many relationship. That is, a row in one table can be linked to several rows in a second table, and a row in the second table can at the same time be linked to many rows in the first table. Consider an example. Imagine creating a database to support a book publishing company. It needs lists of authors and lists of books. Each author may write one or more books. Each book may have one or more authors. How do you represent that in a database? The solution is to represent the relationship between books and authors as a table in its own right. Such a table is often called an intersection table or a mapping table. Each row of this table represents a book-author relationship. Now, each book has potentially many book-author relationships, but each relationship only has one book and one author. So you have converted a many-to-many relationship into two one-to-many relationships. And we already know how to build one-to-many relationships using IDs. And we can find another file in our SQL in the files that are attached. It's called books SQL. And it looks like this, and I'll just close many of these that we don't need anymore. This is how the file looks already. I'm using the file to save a lot of time instead of typing it. So open it up, have a look, go through it, and just familiarize yourself with the file. So if you look at the values inserted into the tables, you see that Jane Austen has 3 books to her credit, while the book, the UML user guide, has 3 authors. So you have Jane Austen here, and one more time, yeah, Jane Austen here, Jane Austen here, Jane Austen here. And the UML user guides has 3 different authors. So if we load that SQLite in a database called books.db. So let's create a database, exit out, and SQLite 3.books.db. So now we have created a new database, and we can read the books SQL, which will load this data into that all this table data into our database. So go ahead and do that. So it creates, it gives this error message, but because the tables not have been created from before, and when it uses the drop command, drop table command, it says no such table. That's what the error message is, but it does the job. So just notice the errors resulting from the drop statements. You always get those the first time you can run the script because the tables don't exist yet. So let's find out which Jane Austen books are published. So it gives us where the books, all the books that where Jane Austen is the author. So things are getting a bit more complex, but if you sit and work through it, you'll get the idea soon enough. Notice you need to include both of the reference tables, book and book author, in the table list after the select. The third table, author, is not listed here because it is listed against its own embedded select statement. So let's try the other way around to see who wrote the UML user guide. Sorry guys, another typo. Just had to get the in front of UML. SQL doesn't search the string. It has to have the correct input to give you the correct feedback back. So if you look closely, we see that the structure of the two queries is identical. We just swapped around the table and field names a little. So that's enough for that example. We'll return in the next section. We'll return to our lending library with the tool hire example. So you now see how you convert it from file-based storage to a full SQL database. Now we're going to build an accompanying Python module that enables application writers to ignore the SQL and just call Python functions. So in the next lesson, we are going to migrate our Lendy database to an SQL database. So hope you enjoyed this lesson, and see you in the next lesson. Okay.